Hello everybody, this is Mr. Navarrete, and today I'll be going over the kinetic molecular theory homework. So, let's get started. Our first question asks, well, if there are two ideal gases and they're both at the same temperature, what else can we say is the same for both of them? Well, if they're at the same temperature, we can also say that they're going to have the same average kinetic energy. Now this leads us on to question 2. For question 2 it asks, if both ideal gases are at the same temperature, what can we say about the velocities of their particles? Are they going to be the same? Are they going to be different? And what we can say is that they're going to be different. Not only would they have different masses, but what we can measure is the average of all of the particles. And while the individual particles might all have different velocities, their average is going to be the same. For 3, there's various parts, so let's take it part by part. Setting up our scenario, it says there's a 5-liter container that contains 2 gases, helium and argon. Both are at standard temperature and pressure. Which of the following will be the same for both gases? And if they're different, which one will have the greater value and why? Here we have to see, will the average kinetic energy of the particles be the same? In short, if they're at the same temperature, that they're going to have the same average kinetic energy. Now it asks, which of the two, between helium and argon, will have a higher velocity of its particles? And in this case, helium is going to have a higher velocity. Why? Well, this is going to be based on their mass, and helium will have a higher velocity because it is lighter. Remember, the heavier our particles, the slower they move. Now we have to see how many moles they're going to have of each one. Will there be different? Will we have more of one? And in short, we're going to have the same number of moles. We're going to be in standard temperature and pressure. Temperature is going to be the same. Pressure is going to be the same for each one. So that means we're going to have the same number of moles. Now D it asks, well, which is going to have a higher mass of the particles? And even though we do have the same number of moles, we're going to have, argon is going to have a higher mass of particles. Why? Well, because it has a higher molar mass. And now for D, we have to see which of these has a higher density. And in case you forgot what density was, it's mass over our volume. While we do have the same volume, what's going to be different is our molar mass. So between helium and argon, which one's going to have a higher density? Argon. Why? Well, because it has a higher mass. For 4, we have to write down the 4 statements that describe an ideal gas. Let's go down the list. Our first statement is, volumes of particles are negligible. For 2, well, it says particles are in constant motion, and the pressure that we see is caused by the collisions of those particles. Our third one, particles do not interact with each other. And 4, the average kinetic energy of the particles is proportional to their temperature in Kelvin. Out of those 4, which one of those postulates is not totally accurate, and why? Well, to be exact, it'd be postulate number 1. Gases do take up a volume, so we can't just simply ignore it and say that it's not there. But what we can ignore is the individual volume of the specific particles. For 6, it asks, what are the conditions under which a gas behaves the most ideal? Well, there are 2 conditions, higher temperatures and low pressure. Why these 2? Well, at higher temperatures, our particles are moving so fast that the intermolecular forces between each of the molecules is going to be negligible. Our kinetic energy is going to be a lot higher than those forces. And at low pressure, well, the collisions, there's going to be so many of them, and we can just focus on how our particles and gases are interacting with each other. Now we have to define the difference between diffusion and effusion. Well, to get us started, diffusion is when gas particles distribute over a larger area. Similar to as if you were holding a gas in a box with like a cover in between, only confining it to that section of the box and then just removing it. Now that the divider isn't there, our gas can diffuse into the whole volume. Effusion, on the other hand, is when a gas goes through a small hole. So in this case, particles are going to be going from one section to another through a hole. Lighter and faster particles are going to be able to go through that hole a lot easier than our slower, bigger molecules. Now we're going to define Graham's law. According to the textbook, Graham's law tells us that the rate of effusion is inversely proportional to the square root of the mass of its particles. But what does that mean to us? Well, it tells us that molecules with higher molar masses will move slower, and molecules with lower molar masses will move faster. Now we have to find the two factors that are important in determining how fast a gas will effuse. Well, our first one is temperature. Temperature tells us how fast our particles are going to be moving. Higher temperatures means there's more kinetic energy, meaning that it can go and effuse faster. Our second one is mass. Particles that are lighter are going to move faster versus particles that are bigger, they're going to move slower. Now let's do some calculations. Here it's asked, an unknown gas diffuses 1.66 times more rapidly than CO2. What is the molar mass of the unknown gas? First thing I'm going to do is write down my equation. The square root of my mass of A divided by my mass of B is equal to the velocity of B divided by the velocity of A. And this fraction here can just be a ratio. Plugging in what we know, well, I'm going to say it's the square root mass of my unknown, that's what I'm trying to figure out, mass of CO2. And since this is just a ratio, I can say that that's going to be 1.66. Doing some algebra, I'm going to get rid of the square root sign. So I'm just going to get mass of my unknown divided by my mass of CO2 is equal to 1.66 squared. Doing some more algebra, I'm going to solve for my mass of my unknown. My mass is going to equal to 1.66 squared times my mass of CO2. And now I'm just going to plug in my mass of CO2. So now my mass of my unknown is going to equal 1.66 squared times 44 grams per mole. Plugging that into my calculator, I get my mass of my unknown to be 121 grams per mole. For 11, it asks, a sample of hydrogen gas diffuses through a porous container 9 times faster than an unknown gas. Estimate the molar mass of the unknown gas. First thing I'm going to do is write down my equation, just replacing A and B with what I was given in the problem. So I get the square root of my mass of my unknown divided by my mass of hydrogen is equal to the speed of my hydrogen divided by the speed of my unknown. In the problem, it tells me that it's moving 9 times as faster, and this is just a ratio. So I'm just going to substitute 9 for that ratio. I'm going to solve for the mass of my unknown. So I'm going to square both sides and then multiply by my mass of hydrogen. So I get the mass of my unknown is equal to 9 squared times 2.02 grams per mole. Plugging that into my calculator, I get 200 grams per mole. For 12, it asks, how much faster does hydrogen escape through a porous container than sulfur dioxide? So again, I'm going to write down my equation with my values in. My speed of my hydrogen divided by my speed of my sulfur dioxide is equal to the square root of the mass of sulfur dioxide divided by the mass of hydrogen. Here, what I'm solving for is for this ratio. So I'm just going to plug in my masses and see what I get. Plug in my masses, I get my ratio is going to equal the square root of 64.01 divided by 2.02. Plugging that into my calculator, I get 5.63. What does this ratio tell me? Well, this tells me that my hydrogen is going to be 5.63 times faster than my sulfur dioxide. For our last one, it asks, what is the rate of effusion for a gas that has a molar mass twice that of a gas that effuses at a rate of 3.62 moles per minute? I might take a couple of reads through the problem to see what's going on, but it's not as difficult as it seems. First thing I'm going to do is write down my equation. My velocity of A divided by my velocity of B is going to be equal to the square root of the mass of B over the mass of A. Now I'm just going to write some notes down based on the problem so that I know what goes where. First, well, my problem says that my mass of one gas is twice as much as the other. So I can say my mass of B is twice as much as my mass of A. What else do we know? Well, we said that mass of B is twice as much as the mass of A, but then it says that that gas will effuse at a rate of 3.62 moles per minute. So we can say that the velocity of A is 3.62 moles per minute. So now when I plug in my values, I get 3.62 divided by the speed of B is equal to the square root of 2 times the mass of A divided by the mass of A. Looking at my equation, I can cancel out my masses of A. So then now all I'm left with when I solve for the speed of B is equal to 3.62 divided by the square root of 2. Plugging all that into my calculator, I get a speed of B of 2.56 moles per minute. And that's it. If you have any questions, don't forget to message myself or Mr. Morgan on Schoology. But other than that, stay safe, and I'll see y'all next time.